working. So I've added a small program here. We have a circle class that implements some kind of interface that's empty for now, and we have a rectangle class that also implements some kind of interface, and we have a interface, and we will have this get area function in it. So in the circle, we need to add this also, and I will share the screen. Boop. So circle. How do you calculate the area of a circle? All right. Return m radius times 3.14 times 3.14, 15, 16, is it? Private. Okay, yeah, okay. Radius. So, and let's have the rectangle also. Maybe it's not that much to copy. Width times height. All right, something like that, and inside the program we can do like this: public static void print area. And we can, of course, now print area circle print area. So, all right. I don't think you think this is quite strange in any way. We have an interface for the types of shapes that we have in our application, and we have this get area operation in the interface, and we now can make functionality that is oblivious of the type of shape that we send to it. So this print area function is our client, so we would not like to change this. We can imagine that we have a lot of advanced code here, or maybe it's inside some code that is actually locked in some way. It could be part of a library, so we can't change it. Could be that it's so messy and advanced, so changing it will be really bad. And our problem now is that we would like to not only calculate the area of a simple shape, but rather of a shape that is more complicated. For example, a rectangle and a circle. So we would like to have the total area calculated. And this collection of objects or should also be dynamic. So we don't really know what type of shapes the user is creating, but we would like to be able to display the total area of this complicated shape that could be any combination of rectangles and circles or any other type of shape that we have in our little hierarchy. And this would of course be problematic because we can't add them to a list, because that would mean that we would need to change our client code. Then this code would need to accept some kind of a list here instead. And we can't do that. We don't want to do it, or we can't do it. So the next pattern to the rescue is the composite pattern. How can a client treat a collection of objects as a single object? And this is exactly what we want. We want our print area function to treat the complicated collection of circles and rectangles as a single object. We can also think about this as something like this, that we can have. Where do we have the shapes? Here we have them. So we have a circle, and we have a rectangle. But in an application like this, we can also kind of like group these. So we have this complicated set of shapes, but we can treat them as one single object. And if we ungroup, we can have the same operations on the parts of the group. And we can have groups inside of groups, and so on and so forth. Another way to think about this is to think about the file system. We have files and we have folders. And we can put files inside of folders, and we can put folders inside of folders. And if we issue a command, delete, for example, on a file, the file is deleted. If we issue the delete command on the folder and all of its contents is deleted also. So we're treating this complicated structure of objects as just one simple object. So that is what the composite class does. And to do this, we create the composite class that realize the common component interface. In our example, it will be the eye shape interface. So the composite should realize this component interface. We let the composite object handle many component objects, leaves. So inside the composite, we can add new shapes to be handled inside of this function. And when we call the getArea function and we happen to be inside a composite, it will forward the message to the objects it contains. So it will ask the objects in its internal list or whatnot for their respective area. So the structure is something like this. We have the component interface with some operation. In our case, we have this eye shape. And in our case, the leaf is circle and rectangle that implement the interface currently. Our client is this small operation print area. And we will now add the composite that will fulfill the interface at the same time contain other implementations of this interface and have add and remove functionality. So this is what I will do now. This is the code that we will not change. So if I change that, I'm cheating. And we can't have that. So let's just add the composite. So the first step, realize the interface. We need to handle our internally the composite should contain other types of shapes also. I'm just using a linked list for now. Maybe this should be linked list. We need to be able to add. I won't implement remove because it's not needed, but often you need to have a remove functionality also. And finally, we have the getArea. And forward to the objects that are in the list area. Public. amazing. And now to send this more complicated object, we of course need to create it. So we can now have a complicated object structure sent to our print area function without changing it, and we could get the total area of these instead. So this is the composite pattern, the basics of the composite pattern instead. So we can let the client, it does not know if it's one shape, 5 shapes, if it's a composite inside a composite, or any other type of complicated structure. Pop quiz. What will happen if we do this? So I added the composite to itself. What will happen when we try to print? Well, we will end up here in the get area, and it will iterate its list, and inside its list it finds itself. So it will then again wind up in get area and iterate its list, and there it will find itself. So it will call get area and wind up here again, and again, and again, and again, and again. And finally, what will happen? Yeah, kablamo! And why will that happen? Exactly, we have an endless recursion going on, and what will happen when we have an endless recursion? Stack overflow. So we should get an exception here. Let's see. Yeah. Stack overflow error. So it's quite easy to make these types of mistakes in using the composite pattern. And you will have unforeseen consequences. But yeah, and especially if you kind of like, okay, I'm getting a complicated structure, and then I in some way get some objects from it, and I add objects into another complicated structure, and you don't really know which object is which, and suddenly you have added yourself to yourself in some part of the program, and blammo, in some other function, things blow up. Because this is an error that will happen in the client. So the debugger will kind of like call your attention to this. Okay, why did it blow up when I called this? But then again, the problem is that this one gets called a lot of times, which in turn is caused by this expression. So you can cause the error in one place, and it will show up in some other place. And that's something you need to be wary about. All right, I think we have one more pattern to go. And I think I will talk about it, and I will then do the implementation of it in my office, because time is running out, and we can take a look at it maybe next lecture, and you can take a look at the code. Composite consequences. The clients can now treat collections of objects as a single object. So we do not need to add this list or something like that to our client code, and that's a good thing. Maybe we can't even change it, or we wouldn't like to change it, and adding even more complexity to the client is maybe not desirable. It's easy to add new component realizations. So we can add new types of shapes, and everything will just work. We can put these inside the composite, no problem. Everything is fine and dandy. So it could be also overly general. What if two special types of leaf objects do not mix well? What if you can't really have a collection that contains both a circle and rectangle for some reason? The composite pattern will let you do that, and this can be a problem. And also it could be problematic to know where to put this, the interface for adding and removing shapes from the composite. Should we have it in the composite class only, or should we move that up to the shape interface? What if some client needs to be able to find the composite itself and add more shapes to it? Then things can become more or less complicated. Creation of the composite structure is always problematic. To create the object hierarchy can be messy, and put the objects inside the composite, and maybe different types of composites inside the composite, and so on and so forth. And as you saw, mistakes can happen quite easily, and will be hard to find maybe the source for them. Okay, the next pattern we will talk about, and I will do the code in the office and you can take a look at it, is the visitor pattern. So how can we add functionality dynamically to a class hierarchy? We could imagine in our case that, okay, we would like to print the type of shape that we have. So when we encounter a rectangle, it should say rectangle area is, and when we encounter a circle, we should say circle area is, and when we encounter a composite, we should say, well, the group area is, the total area is, or something like that. So this is not maybe something that you would like to add to the interface. We could simply add a function print shape name or something like that to the interface itself. But for example, if we do model view controller pattern for architecture, it's not good to add system out print lines inside the model. So for other reasons, we don't want to do this. So the idea then is to use the visitor pattern instead, and this will let us add functionality to our class hierarchy dynamically. So instead of adding it to the interface, we will create a visitor operation in the interface, and this accept method in the shape interface in our case will accept the visitor, and then for each and every type of concrete shape class, we will have a function in the visitor interface, and in the rectangle class, we will visit the visitor and use the rectangle as the argument. This is kind of like a little bit magic and backwards, and not that easy actually to understand what happens here. So the structure looks something like this. So we have our shape interface here. This is I shape. It has its get area and other functionality that is needed. But we then add this accept operation. So each concrete element needs to accept the visitor and do something. So the circle will need to accept the visitor, and the concrete, the rectangle will need to accept the visitor. So, and then we will create a visitor pattern, a visitor interface, where we have concrete operations for each type of element that implements the I-shape interface. So here we will have visit rectangle, and we will send the rectangle in as an argument. And we will have visit circle, and we will send a circle as the argument. So when the circle class, for example, gets the call to accept a visitor, it in turn will call visit circle in the visitor interface. And then we will implement a concrete visitor that will do whatever needed. And now this concrete visitor will know, okay, I get the call for circle, and I know then that it's a circle as the argument. And then I can do my print system out print line area of circle is get area. So by adding this, we can get to know which concrete type we actually have in our abstract class hierarchy. So we can, by creating different types of visitors, we can kind of like plug in functionality into our interface without actually changing the interface. It only has accept. It's kind of magic. But we can take a look at the implementation next time. So by using visitor, we can easily provide dynamic functionality to a class hierarchy. We do not need to change the I-shape interface to add functionality. Instead, we implement different types of visitors. And this could be good because, for example, we would not like to add system out print line in our shape hierarchy, because that will break our architecture. Instead, we can implement this using the visitor pattern. So it's quite sensitive to new classes in the elements hierarchy. For example, if we add triangle, then we will need to update the visitor interface, and all our implemented visitors will also need to accept triangles, and we need to implement these also. However, this is probably better than doing it in some other case, because if we forget to implement in one case, well, the project won't compile, and we know what to do. We need to implement this also. We can have our shape hierarchy as cohesive as possible. It's focused on getting the area and mathematical functionality in our case. We don't need to add a lot of different types of strange functions and dependencies to other things. And it can also be quite hard to know what the visitor actually needs. So in some way, you don't really know what type of functionality you need to add by using the visitor. So this means that you often add accessors, for example, for all types of information. So in our rectangle class, we will add get width, get height. In the circle class, we will add get radius. And maybe this is not good for an encapsulation type of problem, because then everyone can get the area and everyone can get the width and height. And maybe it's only a speculation that, oh, we could maybe sometime in the future we need to have access to this information because someone can use it in some way, and that is always risky to speculatively open up your classes, because someone might need access to this later on. So Visitor. I think actually that is the last pattern. And if you opt for higher grades, at least on the last workshop, you will probably need to use the visitor pattern. I also think that if you opt for higher grades on workshop 2, you should look into both strategy and composite. And in workshop number 3, you will practice a lot using the strategy pattern to add the new types of rules to the game. A short mention about the online exam. We will have an online exam, as I said, during the first lectures. And I think I will test run this system this week. So I will post something on the course homepage, and you should be able to make a short test run of it, and we can see that it kind of like sticks together and works. So if we have any issues, you can let me know using mail or Slack, and we can talk a little bit about it maybe in next week. So that is at least my plan, and I hope last year it worked quite well, and hopefully it will do so this year also. Any questions? Yeah? No, it's online. It's a quiz type of system where you have multiple choice questions, and you will immediately know if you have passed or not. If you have not passed, you can you have the opportunity to add comments to your answers, and then I can take a look at these comments and award you some bonus points if I think the answer is good or not. So it's a multiple choice question where you get a number of questions, and there will be quite a strict time limit. So you will need to know some things by heart. And time will not permit you to look everything up online or in the book or whatnot, because I can't really limit your the help that you can kind of like get anyway. So you're free to use anything you want. Instead, there's a strict time limit and quite a small time limit also. So you cannot spend your whole day trying to figure out the answer for the first question, so to speak. Then you have quite a lot of time to hand in your comments, though. So if you answer something wrongly, you can actually spend some time looking at your answer, looking at the question, finding out if you thought wrong in some way, and you can add your comments. So there you have more time. All right, but you can take a look at it hopefully this week, and we can discuss it also next lecture if there's any problems or questions regarding this. All right, any more questions? Okay, thank you for this week then.